Chapter 11, Fluid Mechanics, Hamid Mazagwalachi, SC Doctor, Farzan Parsanajad, PhD. Introduction. Fluid mechanics is a study of change that occurs in fluid that subject to the forces. Two major decisions with the field of fluid mechanics, fluid static, fluid dynamics. Fluid static is the state of the fluid subject to the balanced forces such as fluid remains in equilibrium condition. Fluid dynamics is a study of motion of the interactions with the fluid with the object that it may encounter. Definition: fluid properties, fluid statics, fluid dynamics, internal flow, external flow devices, fluid measurement, dimensional analysis, dimensional homogeneity, similitude, and summary. Definitions. As with any other field of the subject study, the fluid mechanics has a vocabulary and term that must be understood before the basic principles that are going to be introduced. What is a fluid? Fluid systems of the developed, they deform constantly with shear stress applied with no matter how small the shear stress is. The substance of the liquid form of the vapor phase of the liquid fluid. Control volume. All principles of the fluid mechanism that define the relation with the control volume of the imaginary region space that define with the boundaries of the stationary and move of the general of the material may cross boundary of the control volume. The boundaries of the control volume are completely arbitrary, when possible. They are chosen in a way that simplifies the analysis. Stress, the force upon which a fluid may be categorized either by body force, surface forces, body forces, or forces that act on all fluids within the fluid occur without physical contact, which include the electromagnetic gravitational forces. The surface forces are forces applied directly to the surface of the liquid to the physical contact. Total force per unit acting on the fluid at any of the point in the volume is important in the parameter with have been given the name of the name stress. Stress at point P is defined as stress at point P is equal to limited LMI over the 6A to the resultant of the infestialism area at point A over the force acting in the infestimal area over the infestial area at point P. Both area of the force over the equation 11 and 1 are vector quantities. They have the magnitude of the direction of the quantities expressed with the three components with respect to the same coordinate. Some coordinate system. In general, to describe the stress of the fluid at any of the point with respect to the coordinate system, and the 9 components are required with the P and C. Stress is often expressed as terms of two vector components of relation with the differential area with the component normal to or perpendicular to the is A, the normal stress. For the component A, the component of the differential area is the shear stress. In stationary fluid with the normal stress and fluid with the pressure magnitude with the independent with the direction of the differential area of the shear stress is related to fluid motion. 11 and 2. Fluid properties. Fluid properties are fluid characteristics whose value of the predictive of the reaction fluid with the subject of the applied forces. The list of the follows do not include all possible fluid properties, but define the terms though used throughout this chapter. Velocity. Velocity of the time of the change of the position of the fluid lit particle with the velocity of the fluid's vector field with the quantity for each point with the volume makes of the fluid that can be assigned with the magnitude of the direction of fluid velocity. The velocity of the fluid will appear with the three forms throughout the chapter. These forms as follows. Velocity with the vector of the quantity of the fluid velocity given at point of the fluid, both of the magnitude and the direction associated with the quantity. Speed with the velocity with which the vector velocity is given at a point of fluid, and the average speed is v with the average fluid speed through the surface of the control volume. The Mach number. The Mach number is the dimensional parameter that describes the fluid speed, but defined as rate of fluid speed with the speed of sound. Mach number is equal to the volume of the fluid speed in foot in seconds or meters in seconds over the speed of sound, foot seconds and seconds. And the perfect speed of sound is defined as speed of sound is equal to the square root of specific heat ratio times the gas constant times the absolute temperature of the gas. In the equation, R is equal to a universal gas constant over the molecular weight of the gas. And then perfect gas sound is defined, and it shows acceleration. Acceleration is the time rate of change velocity of fluid particle for the acceleration is also a vector fluid quantity and can act at change with either magnitude of the direction of velocity. Pressure of the two reference value of the pressure with all values of the pressure called the gauge pressure that defined by the reference to ambient temperature and atmospheric pressure. The absolute pressure is defined by the reference of the zero pressure. Two values of pressures related by these equations. Absolute pressure is equal to the pressure gauge pressure plus the atmospheric pressure and examples. Density. With the density of the fluid with the mass contained within 1 unit volume, the density of the fluid is given in the location as fluid density with the limitation of the velocity with the zero, or the mass contained fasciculus volume over the fasciculus volume in foot cubed or meters. Analyzing fluid system is often specified with assuming the density the same of the every point within the volume of the fluid in compressible flow analysis. Specific value for the fluid V, volume of the space occupied by the unit of mass of the fluid, is the reciprocal of the density expressed in volume is equal. Specific volume is equal to 1 over P. Specific weight is the fluid defined as the weight of the unit volume of the relative of the fluid density is the specific weight of the fluid over P times the acceleration due to gravity, and that's at sea level. Specific gravity is dimensional expression of the density of the fluid volume of the ratio of fluid density to the density of the liquid of water at 4 degrees Celsius. So specific gravity is equal to the, where P is equal to 100 kilograms, P over the water, and equal to the specific weight over the water, Y over the specific weight of water. Viscosity. When shear force is amplitude by fluid motion will occur with the magnitude fluid velocity with the relay with the magnitude shear stress with the most of the common fluids. The shear stress within the fluid is directly proportional to the velocity of the gradient. The viscosity is a name given a proportional constant. Viscosity is the fluid shown in how resistant fluids is motion, and it shows this program. TP, shear stress of the differential over the normal direction, is times P, and then shear stress of the differential and normal to the direction is equal to fluid dynamic viscosity times velocity gradient in the direction n. Fluid type called for the Newton fluids, and then should be recognized with an equation 11 to 10 for the given shear stress of the viscosity of the fluid increase with the magnitude velocity gradient decreases. There are many fluids with a two-stage blend, and many of the planes that cannot be classified with the Newton fluid. But for many non-Newton fluids, the shear stress is related with the velocity gradient with the fluid with a power law relationship. Two examples of such non-fluid fluids are pseudoplastic fluids, for which the viscosity increases with the velocity with gradient increase with the delineant fluids, for which the viscosity increases with the velocity and gradient increases for the power law in the non-Newton field. Shear stress of the differential normal direction is equal to K, the constant index, over some V and X to the nth. Surface tension. Surface tension with any of the fluid or a boundary between the two fluids, there is force if it tends to hold surface together. The force is called the surface tension of the fluid and defined with a tensile force between 2 points surface fluid per unit length over the distance between 2 points. So we have surface tension is equal to the force along the fluid surface over the length of the fluid surface. Capillary capillary action or calorimetry is observed with the change of the shape of the fluid with a free surface in contact with the solid wall. The result of the interaction surface tension with the general cohesive forces between the molecules of the liquid. Curved fluid surface with the general forms of the result of the capillary action is called the meniscus, shown in figure 11.2a. In the area of the free surface is larger rather than forming a complete meniscus. The edge of the surface will be covered as shown with the figure 11.2b and c. Whether or not surface of the complete meniscus, the slope of the curve of the well of the tube with the angle contact b. Angle contact indicating the relationship between the surface tension with the cohesion of the force of the liquid with the angle less than 90 degrees and angle 11.2b with the surface tension is stronger than cohesion forces. Angle is greater than 90 degrees and L2c with the cohesive forces are stronger than the surface tension. When small diameter tube placed with the fluid for the surface tension stronger than the molecular cohesive force, the fluid level inside of the tube will raise a certain distance as shown figure 11.2a. Height of the column is given in these equation. Height is equal to 4 times Jesus and H and D. 11.3 Fluid statics. Fluid static is a state of fluid system with no fluid motion, no shear stress. The primary challenge is fluid static is determined by the pressure distribution within the fluid. Hydrostatic pressure. When fluid is moving, the stress acting on each of the fluid particles becomes independent of the direction which is called evaluated. In other words, the stress is defined in equation 11.1. Stress is stationary fluid with the same point with some value with the same no matter what direction of the differential area is taken. The value of the hydrostatic pressure of the fluid at the point. The hydrostatic pressure of the fluid is the function of the height of the volume of the, regardless of the shape of the container, due to the fact that any of the point of the fluid must support the weight of the fluid above it. For any two locations at the same height, the hydrostatic pressure will be the same. This is the principle behind operation of two devices using the hydrostatic pressure manometers and barometers. For control volume shown in figure 11.3, the hydrostatic pressure point B of the fluid is given in these equations. Then it goes into example. Represented by the unit for the term pounds over foot over 32.7 of the pounds over the second is above manometry or manometer illustrated in 11.4 device used to measure pressure difference and is constant U-shaped with the end of each of the one open to the two environments whose pressure we will use to compare. Figure 11.4, difference of the pressure made between the two environments is related to the difference of the height between the two legs of manometers follows. P1 minus P2 is equal to PMGH plus P2GH2 minus P1GH1, or P1 minus 1 P2 is equal to YMKHM plus Y2H2 minus Y1H1. In density specific weight of either fluid 1 or fluid 2, figure 11.4, small compared with the density of the space specified weight with a manometer fluid is the contribution equations 11.17, 11 and 18 being neglected. For example, the fluid 1 is air density 1.23 kilograms of meters cubed. The fluid 2 is water, the density of 1,000 kilograms meters cubed. The manometer of the fluid oil density approximately 830 kilograms of meters cubed. The negative effect of the air can be neglected. Equations 11 and 17, 11 and 18 can be reduced. It's, however, density of the specific weights of both fluids are small compared to the density of specific weight of the manometer fluids. Equation 11 and 17, 11 and 18, P1 2 P2 that equals PMGHM, and P1 minus P2 equals YMHM, with one end of the manometer exposed directly to the atmosphere of the device and an open manometer illustrated in figure 11.5, and equations 11, 17, and 18 apply to open manometer. Pressure 1 is related to atmospheric pressure. For the manometer shown in figure 11.15, with the pressure of the surface of the liquid, P1 is given. And then we go on to density, air, standard pressure, temperature is 1 atm at 0 degrees Celsius or 1.168 kilograms meter cubed. Density of the mercury at the same condition, 13,534 kilograms meter cubed. Barometers. Barometer illustrated in figure 11.6 of the device uses the atmospheric pressure. The atmospheric pressure acts on the exposed surface of the barometer fluid, maintaining the height of the column of the fluid of the tube. Pressure of the empty section on the top of the tube is equal to the vapor pressure of the barometer fluid with the ambient temperatures. Height of the fluid and column related to the atmospheric pressure is the pressure atmosphere, pressure volume over the pressure GHM air, pressure atmosphere minus pressure velocity equals YHM, where PV is the vapor pressure of the magnitude fluid with the ambient tension on the barometer fluid is usually chosen at PU closest to 0. Forces submerged surfaces. Any location surface of the submerged object with the pressure of the point and proportional point distance of the surface of the pressure determined as P equals P to O, pressure 0 at pressure G. Pressure grams Z, the vertical distance between the point and surface of the liquid. For any arbitrary region, surface of the subject objective, the differential area is acted upon the forces acting on differential area surface and submerged object is equal to the fluid pressure at the location of differential surface of the subject or area. Difference of the force normal into the surface of the force integrated with the region of the total force acting with the region between the for a region on a flat plate control volume figure 11.7. Pressure is surface of the fluid and 0 force is expressed as force is equal to force X plus force Y. Force X absolute is equal to P pressure 1 plus pressure 2 over 2 for the area. And force Y is equal to pressure G versus volume area. Equations 1130 and 1132 apply with the contribution of atmospheric pressure forces, submerged force, and negligible. The effect of the total non-negligible. The gauge pressures equal to 1131 should be replaced with absolute pressure, surface force term, pressure, atmosphere, and surface force term added to the equation 1132. The term AH is the horizontal projection of submerged plate in a free surface of fluid. And it goes into a solution. Note that the pressure increases the linear and the depth. Alright, the center pressure, the region of the surface of the submerged rigid body center pressure for the location region through the concentrated point forces force F from the preceding section have the same effect for the submerged body of the distributed pressure force over the entire region. The definitions illustrated in figure 11.8. Coordinate center pressure relative to the centroid submerged area Y and Z is given in the following equation. Y is equal to and then to where the moment of the air axis parallel to the y-axis passing the centroid area of the volume. The value Iy is given in the equation for parallel axis theorem, where it is in the equations 1133 and 1134. Area product in area with the axis parallel to the y and z axis passing the centroid area through the value of momentum area and axis parallel, given in the equation from the parallel axis, where from the values of moment of an inherit from the inherit, several common shapes can be found in the dynamic chapters, chapter 8 of this book. And then it goes into examples and foams. Y and Z can be used to coupling moment of pressure force about pointing line about a point or a line hinge on a surface. Archimedes' principle of buoyancy. Any object completely partially submerged will experience buoyancy forces. Forces directed direction opposite of the wave of the object, which result of the total pressure force of fluid acting on the submerged body. According to Archimedes' principle, the magnitude of the buoyancy force is equal to the wave of the fluid distance by the object. The object is floating on the surface of the liquid. It will displace the volume of the fluid that has the same weight as the object. Solution. In general, the volume velocity cubed is replaced by the total volume of the object of the fluid. So buoyancy of the force buoyancy is equal to the pressure of the water over the weighted volume of the object in cube grams. Weight of the cube counteract the buoyancy, so the total resultant force is the axis of the cube. Total minus buoyancy of the mass in grams. 11.4 Fluid dynamics. Fluid dynamics is the state of the fluid motion when they interact with the fluid of the objects that may encounter the basic principle of mass energy conservation. Newton seconds. The law of the motion applied with the fluid system allow for the prediction of the fluid characteristics. Conservation of mass and the continuity equation. Every fluid system and its mass is conserved, and conservation shall be stated in terms of the mass equation as dm over dt of this CV is equal to mm in inch, measure in mass in, mass out. Common class of fluid problems, steady state problems, values of fluid properties. Control volume did not change from steady state to control volume. Mass over temperature with a constant volume is equal to 0. So mass in equals mass out. For arbitrary control volume shown in figure 11.9, conservation mass is mass 1 is equal to mass 2, where mass 1 is the mass flow rate with the cross-sectional area of the control volume 0.1, and mass 2 is the mass flow rate for the cross-sectional area of the control volume at 0.2. Equivalent expressions of 1142 shows PA1 A1 volume 1 equal to P2 A2 volume 2. A1 cross-sectional area, P1 Q1 equal to P2 Q2, A1 cross-sectional area control volume 0.1, A2 cross-sectional area control volume 0.1, V1 average fluid speed at 0.1, V2 average fluid speed at 0.2, Q1 Q2 volumetric flow rate at fluid entering 0.1 and N2, in the flow incompressible value of the density and constant conservation mass continuity equation, as is volumetric fluid rating of the fluid times the cross-sectional area of volume 1 is equal to the area of cross-sectional area of volume 2 and volume and the average fluid speed 2. In impulse momentum principle. Newton's second law of the forces of the mass of the acceleration can be applied with the fluid systems with the principle known as impulse momentum principle. The principle expressed mathematically in control volume as follows, where logarithm of rate of momentum entering and leaving the control volume is equal to the mass volume times c, the control volume, equal to the total external force acting on the control volume. The state system changes to momentum of the control volume can be expressed as dp over dt, control volume equal to dp over dt, control inches and equal to in and dp minus dp out. Therefore, your mass of velocity in is minus the mass velocity out, so that you get the forces of the mass velocity in minus mass velocity out. An impulse momentum principle can be applied in case of pipe bending, enlargement, and contracting, finding of the tool force exerted on a fluid such as a device. From Figure 10, free body movement of fluid and general pipe bending, enlargement, contraction. Equation 11 to 46 can be applied to control volume described in 11 to 10. Produce these equations. These relationships are valid both at compressible and compressible. Absolute value of Fx is equal to mass volume 1 plus the pressure at area 1 plus mass volume 2, mass velocity 2 plus pressure 2, area 2 cosine A. Absolute F of force Y is equal to W minus mass volume 2 minus pressure 2 AM2 sin A. And then it goes into example solution. Conservation of energy for the Bernoulli and fluid equations, where the continuous steady flow of the idea of the conservation of energy expressed using the Bernoulli equation, also known as field equation, expression conservation energy, we're neglecting frictional loss applied with the two sections on the streamline. The Bernoulli equation is expressed as pressure 1y over the plus velocity 1 squared over 2 grams plus z1 equals the pressure 2 over y plus v2 squared over 2 grams over the velocity 2. With the Reed flow will experience frictional loss, which new on account of the Bernoulli equation 11 to 51 can be modified to include the effect of the frictional loss as follows. And then where HF the major head loss volumes of the determined numerical relation flowing with the horizontal pipe constant cross-sectional area equation 1152 reduces. So major head loss is equal to pressure 1 minus pressure 2 over Y. And it goes into solutions and examples. Alright, static versus stagnation pressure. The pressure of the Bernoulli equation, static pressure of the fluid. The pressure would be measured with a device to move the fluid. With the stationary device with the measure pressure of the moving the fluid with the reduce. Read the differential pressure measuring the stagnation pressure. The relation between the static pressure and the stagnation pressure fluid can be defined by the Bernoulli equation. P0 over P equals to the PS over P plus V2 over 2. Or P0, stagnation pressure is equal to the static pressure of the fluid over plus 1 over 2 times the pressure of the volume, the speed of the fluid point where the measure is taken to squared. Grade line hydraulic gradient energy line. If the pipe is fitted with a tube with an open manometer along the length of the static field with the pressure location can be visualized with the flow fluid pressurizing success location will be lower as shown in figure 1111. The measuring line drawn through the medius of the manometer with a line with a grade line hydraulic gradient. Alternatively, the hydraulic gradient can be thought as the plot of the static pressure function distance along the pipe. The stagnation pressure rather than the static pressure of the fluid flowing through the pipe, plotted at a function distance along the pipe line. The resultant energy line shows the hydraulic gradient direction of fluid. Description of hydraulic gradient. Reynolds number. Reynolds number RE, the non-dimensional number, characterized fluid flow with the ratio integral force of viscous forces acting on the fluid to define. Reynolds number is equal to the pressure of the speed of the fluid at D over the U, and Reynolds number is equal to V over the D over V. V is the kinetic viscosity defined as U over U over the P. Parameter D is equation 1156 and 1157. The characteristic length flow over the tube is the characterized length of the pipe diameter flow over the flat plate. Characteristic length of the plate and direction of the flow for power of law of non-Newton fluid. The Reynolds number is defined as Reynolds number of the pressure over the velocity 2 with times the parameters to the nth times parameter nth. over consistency index of the 3 n plus 1 over 4 n times 8 to the n minus 1. Alright, laminar flow. A fluid flows begins from a raft of fluid, highly organized streamlines or smooth with a continuous of the fluid particle with both parallel to the means of the bulk flow. With the type of the flow with the laminar flow generally occurs in fluid flows below Reynolds number of fluids with high viscosity and low density flowing at low speed. Laminar flow with the fluid flow can be thought as a collection of fluid layers. Each layer is a fluid particle with moving through the same velocity. There is no macroscopic mixing of fluid layers. Turbulent flow. A flow rate increase with the general character of the flow and begin with a significant random three-dimensional fluctuation. Fluid flow velocity with the beginning to appear superimposed over the local mean of the flow velocity. Type of the flow of the turbulent flow results in significant fluid mixing. Lowest Reynolds number with the turbulent flow can be expressed with the critical Reynolds number, or REC. The flow of the pipe, the value of the Reynolds critical number to approximately 2300. Pipe flow of the Reynolds number greater than approximately 4000 flow is considered fully turbulent. Range of the Reynolds numbers between these limit is a transitional region with the difficulty to predict the type of the flow which will occur. 11.5 Internal flow. In this section, we consider the flow flowing from a closed pipe of the duct. The experimental observation shown with the fluid particle with the adjacent of the wall of the pipe with the fluid arrow velocity. This is called no-slip condition. No fluid slipping against the wall of the pipe with the maximum fluid velocity occurs along the turn line of the pipe. Variation fluid velocity with the cause of the viscosity, force of the fluid, and shear forces between the fluid particle. The shear forces perform works against the moving fluid, reducing the fluid energy travel through the pipe. The loss of the energy due to friction, often called the head loss, is observed with a drop of the fluid pressure on the pipe. As fluid enters or leaves the pipe, the internal passage velocity profile of the passage is functional. It was a function fluid location along the length of the passage geometry of the opening far from the entrance that exists, and however the velocity profile becomes uniform at any position along the length of the pipe, independent of the entrance-exit geometry. Flow in the region is fully developed. Fully developed linear flow is illustrated in Figure 11.12. The velocity of fluid particle in the pipe, the function radial location. Particle in the pipe, the pressure drop through the pipe is resultant pressure of the length. Some of the relationship of the flow, some of the pressure of the laminate, shall we say, or pipe, some relationship of the flow that follows. Speed distribution VR is equal to R2, negative R2 plus over 4U times pressure over the length times 1 times R over R squared. Average speed viscosity of Q over A equal to R2 minus A negative 8U times pressure over the length. Maximum speed, volume max, volumetric, shear strength distribution. R is radial coordinate system with the origin center line of the pipe. R is the inside radius of the pipe. The Darcy equation. To estimate the frictional loss and flow of the horizontal pipe with the constant cross-sectional area of the Barrons equation is reduced pressure 1 minus pressure 2 of the pressure grams of the head static over the equals Y head static frictional head loss of the estimated during the Darcy equation head loss over the equal to the frequent flow of L over D times V velocity squared over the times 2G. Linear flow is friction factor is 64 to the Reynolds number. The transitional turbulent flow can be Modi standard diagram, copy of which is included at the end of this chapter. Another parameter required with a Moody diagram relative to the roughness is E over D. Roughness of the E of the pipe of the function material of that process of which pipe is manufactured. Some example of the roughness value of the table 11.1. And then it goes into example solution. Hagnan's Priscilla equation, pressure law of laminar force circular pipe related to the volumetric flow rate using Huygens Pascal equation. Volumetric flow rate is equal to the pi times inside radius of the pipe to the fourth times the resultant pressure drop in the pipe of the fractional losses over times 8U UL, or volumetric flow rate is equal to pi times the inside diameter of the pipe times the resultant pressure and drop in the pipe due to the frictional losses times 18 to the UPL. Head loss and pipe bend enlargement, contraction, entrances and exits. Minor head losses occur at any time inside of the direction pipe change of the value, but the minor head loss can be used as the following. Minor head loss is equal to volume squared over law of coefficiency times 2 to the gram, determined by a geometry change of area grade flow of the table to commonly use to determine the loss coefficients. Figure 11.3 given the loss coefficient, some type of the entrance exits. Funeral sequential modified valve will determine change of the energy fluid flow through the pipe, including both major and minor. Multi-pipe path pipeline. Common technique used to increase capacity of the pipe is to add another pipe in parallel. Possible predict how much fluid in which will flow each path. Fluid pressure before each branch must be equal. Therefore, the flow divided itself may such pay with a head loss through each path will equal the multiple pipeline paths shown in Figure 11.14. Head loss equals head loss friction 1 equals head loss friction A equals head loss friction B. For continuing equation, when the flow rate, fluid entering, control volume, diameters, lengths of pipes are known, equations 1172 and 1173 can be solved simultaneously determining the velocity A and B. An example 1116 solution. Flow rates, non-circular ducts. Non-circular ducts can be utilized with the same technique round ducts, although it's needed to replace with a tube diameter, new parameter called hydraulic radius or hydraulic diameter. The equations of the parameters are followed. Hydraulic radius is cross-sectional over wetted parameter. Hydraulic diameter is equal to 4 times the cross-sectional area of the wetted parameter. For instance, Reynolds number of the flow with a non-circular duct. Reynolds flow number in a flow of the non-circular duct is equal to pressure times the viscosity over the diameter. Hydraulic diameter over U. Open channel flow. Relation will develop until they have an inflow inside of a closed pipe with a much such of the Darcy friction factor have been determined through the experimental basic geometry fluid system analyzed change of the expected need with a new empirical relation with such relation with the open channel 3. There is a free surface flow with a Manning and equation with a Hazen-Williams equation. Manning's equation volume is equal to 1 over the times n to the r to the third over 2 to the r 2/3 times s to the 1 over 2. Hazen-Williams equation is volume is equal to 0.849 of the Hazen-Williams roughness coefficient hydraulic radius channel 0 to the 0.63 and slope of the energy grade line 0.54. 11.6 external flow. Often important external flow analysis, totally drag force object study of the drag is measured with the non-dimensional coefficient drag. Non-dimensional coefficient drag is equal to the total drag force exerted on the object by fluid times divided by 1/2 the density of the fluid times speed of the fluid far from the object squared times the area over the drag force is acting. The coefficient dragging is given the drag force as the calculated as total drag force exerted on the object fluid times the non-dimensional coefficients drag on velocity, speed of the fluid times squared times the area of the cross-section divided by 2. Uniform flow over a flat plate. Flow over a flat plate demonstrates the concept important to the study of the fluid dynamic. So the boundary of the layer fluid flow encounters first diagram plate vertical flow distribution uniform shown in Figure 11.15. Fluid progresses along the plate vertical distance above the plate with the fluid with speed, velocity encountered increase the distance with a count of the boundary thickness. The boundary layer of the fluid, velocity, shear strip of the fluid vary with the distance above the strip of the plate with the characteristic length give the uniform flow of the plate length of the plate. The Reynolds number to flow over the flat plate is shown as Reynolds number at length times pressure, volume, velocity of first encountered length over U. Coefficient drag over the flat plate with the given in these equations. And then we'll go to 11.7 devices. Principle of fluid mechanics discussed so far can be used to describe operations of industrial devices. For example, these few examples of deflector blades. Marine devices, kinetic energy, high velocity fluid, produce power, which is commonly transmitted shear with the curved surface of the blades and pull with the momentum principle used to describe their operation. We will note the viscosity of the drag of the fluid with the blade surface, therefore the fluid leaving the trailed end of the blade will have the same speed as the fluid approaching the leading edge of the blade. Fixed blade show the fluid jet acting on the stationary blade Since the blade does not move with the direction of the fluid stream leave the blade, it is determined the angle of the traveling edge of the blade with the blade's reaction related to the change of the moment of the fluid assumed with the speed of the fluid stream leaving the blade is equal to the speed of the fluid stream entering the blade. And that shows the solutions. Alright, so the moving blade is moving in the same direction of the fluid jet and capable of rotating portions of the in-bow machinery velocity of the blade effects. Change of fluid momentum of the occurs the situation is figured in 1117. Fluid jet overing the moving of the blade. Relationship between the velocities, forces, of blades are given in the following equations. Alright, an impulse turbine shown schematically figured 11 and 18. This the blades locally readily around when the fluid strikes the blades. Tangent of the turbine reaction force of the fluid against the blades begins to turn over the bow and the axis of the motion with the U of the generated power. The amount of the power generated related to the angle of the blade deflection. A maximum power is related to 180 degrees of the turbine power is related with the mass flow rate with the fluid velocity by the equation. And then examples. These relations are valid for the compressible and incompressible fluids, where A is 180 degrees. The weight is the speed of the blade is rotational speed of the turbine equal to VB square root of radius of the turbine times the rotational speed of the turbine. Alright, jet propulsion. Fluid U of the propulsion example, the particular U of the impulse and momentum, the moment of the fluid leaving the control volume results in the force acting with the control volume direction opposite of the fluid jet with its destined decree described in 11 to 19. Potential energy fluid is converted with kinetic energy as fluid flows out of an orifice of fluid is expelled that leaves the system with a certain amount of the momentum as a result. Force is exerted down with the control volume in the direction opposite of the flow of the orifice. The force is given as force of the QP quantity pressure volume average speed of the flow through the zero, or force times P times average speed flow through the nozzle and times the cross-sectional area. By applying Barrons' equation between the three surface outlet systems, we can calculate the force. Pumps are useful mechanical energy, increase the energy flow with the amount of energy added to the fluid per unit of time is expressed. Pump is where P is equal to pump power and volumetric flow rate is pump times the Y to the change of the fluid and head. Basically, the influence of the pump at the amount of the energy pump supplied in the pump something greater than the amount of energy transferred in the pump. The ratio of the pump and the transfer of the fluid power of the pump is pump sufficiency. The amount of power must be supplied to the pump can be found in this equation. Pumps required is equal to volumetric flow rate Y times the head. Change in fluid in the head over nth. Art 11.8 fluid measurements. The number of the devices that are developed allow for the measurement of fluid velocity, fluid rate. For a few moments, take a few moments to the most common type described below. Pilot the two devices measure the stagnant pressure moving fluid with a tube within a small diameter hole with the end of the pointed directly fluid flowing in the figure 1120. Fluid flow is complicated with the stagnant pressure of the square root of pressure 2 times pressure 0 minus pressure second pressure strains. Or you have your orifice flow meter. Orifice flow millimeter is illustrated in 1121. Flat plate, small hole, center plate placed in the pipe. Pressure measurements are taken fixed location upstream and downstream of the orifice flow rate of the fluid is related to the difference in value of the upstream and the downstream measurements. Volumetric flow rates, flow meter coefficients is examples. Alright, a venturi flow meter like an orifice flow meter. Venturi flow meter illustrated you with the pressure drop across the flow restriction known as the geometry measure flow rate. Volumetric flow rate, the venturi flow is given as coefficient value. C V is experimental with a gradual contraction venturi flow meter with a largely reduced head loss fluid stream. Shape of the device, however, the much more complicated the manufacture in an orifice. Submerged orifice of the rate flow with the submerged illustrated with the figure 1123 related with the hydrostatic pressure each side of the orifice shown in the equation 11.106 and 11.107. Orifice of discharge into the atmosphere fluid, the downside of the orifice of discharge of the emitted temperature illustrated with the figure 1124, atmospheric contribution equation figure 1108 and 1109. Neglective of the flow rate is the flow rate is equal to the coefficient of the area of the square root of the grams times the head, gallons of the head loss. Alright, 11.9, dimensional analysis, dimensional homogeneity. Dimensional homogeneity is a relationship that is one whose value is independent of the fundamental dimension, units of the mass measure, the length of the time. Dimensional homogeneity is sure of the relationship of the play for the dimensionalist of the Buckingham P.I. Thermo tells the how many dimensional the groups of the described relationship that can say with the relationship with the n independent variable to move the r different fundamental dimensions, mass, length of the time, thus n minus r dimensional groups are required. Art 1110, similar to model testing of the large role of fluid dynamic on with the region of the equation fluid flow, significantly efficient, complex, impractical to solve them, all the simple flow with the condition of the flow. Furthermore, testing of the full cycle of the parameter type is often prohibitively expensive. We can assure the model we use the testing predictably accurately with the fluid interaction full-scale prototype, which can prove the similarity between the 2 and 3 kinds of similarity required. Geometric similarity with the model has to have the same shape of the full-scale prototype. Each of the geometric parameters described in the shape of the side of the model differs for the corresponding geometric parameter of the full-size scale prototype of the constant scale factor. Kinematic similarity with the character of the fluid flow must seem with the model with a full-scale prototype and other but the direction flowed. Each of the fluid particle in the near of the model must be the same as of the fluid particle with its corresponding location near the full-scale prototype of the velocity of the 2 corresponding fluid particles must be related with a constant scale factor. Dynamic similarity, those forces that interact with the model must be similar to the forces that act on the full-scale prototype. For each forces act the full-scale prototype of the corresponding acting model, but the corresponding must act the same direction, therefore the corresponding location of the magnitude with the difference of the constant scale factor of the model and prototype must have the geometric kinematic similarity. Dynamic similarity is to be achieved with the dynamic similarity is achieved with the following conditions. And then we'll go into the subscript P with a full-scale prototype and then subscript M for the model. 11 is summary. In this chapter, the principle of analyzing problems in fluid mechanical. To discuss the chapter start with the definition fundamental institute of the fluid mechanics, presenting the 2 categories problems: hydrostatic study of fluid tests at rest and dynamic study of fluids at motion. The discussion of hydrostatic concept of the fluid pressure, buoyancy, barometry presented with the following with the fluid dynamics problems with the conservation law of the mass balance of the momentum balance, the energy balance falls in this category. Finally, methods of the study applied in engineering problems such as calculations of the head, energy loss pipes, and analyzing turbo machinery were discussed. Chapter 12, Electricity and Magnetism.